In the last couple of lectures, we set out to prove the Cayley Hamilton theorem. So we first started by defining the so-called minimal polynomial, which is a polynomial p such that p of a equals 0, is equal to 0 matrix. In the last lecture video, we looked into similar matrices and how it represents a change of basis. So if we have two matrices A and B, and where A is perhaps the linear transformation with respect to the standard ordered basis, then the matrix B represents the same linear transformation with respect to a different ordered basis if A equal to VB V inverse, and the columns of V basically represent the basis vectors with respect to which B is specified. So and along these lines, I defined the so-called fan and a fan basis. So a fan is basically a sequence of subspaces, a nested sequence of subspaces where which is invariant to the transformation. So A times that particular subspace lies within the subspace. And a basis for such a fan is called a fan basis. And we show that if there exists a fan basis, then the corresponding linear transformation with respect to the fan basis is a triangular matrix. And in this particular lecture video, I'll show that for every n by n matrix, there exists a fan, and therefore every square matrix A is similar to a triangular matrix. And once we have this, we'll see a proof of the Cayley Hamilton theorem in terms of triangular matrices. All right. So what we want to show is that every square matrix is similar to a triangular matrix, right? And in particular, what does this mean? It means that for every n by n matrix A, we can find a nested sequence of subspaces. So we can find subspaces V1, V2 up to Pn, where the dimension of Vi is equal to I, and Vi is contained within Vi plus 1, and moreover A times Vi is a subset of Vi. So if you take any vector x from Vi, then A times x also lies within Vi. And this is equivalent to saying that there always exists an invertible matrix P such that A equal to P inverse, where this T is triangular, is upper triangular. So that's what we want to prove. The proof is pretty simple. It uses a mathematical induction. So of course, this statement is trivial for a 1 by 1 matrix. So any 1 by 1 matrix is obviously upper triangular. So it's trivial for n equal to 1. Right. So now let's assume that it's assume that this is true for n minus 1. Right. So for all I equal to 1, 2, 3 up to n minus 1, every I by a matrix is similar to a triangular matrix. So basically you can find a basis, you can find a fan basis for all linear transformations n by n matrices A. Okay. Now consider any square matrix A, n by n, right? So we want to somehow reduce this to an n minus 1 by n minus 1 matrix, and so that we can use the induction step, right? And to do that, let's take the following basis. So since A is an n by n matrix, let's take any eigenvalue, any eigenvalue of A, and suppose that V is a corresponding eigenvector. So V is a non-zero vector such that A times V equal to lambda times V, right? So we can extend this eigenvector into a basis for Rn. So out of which only the first vector is the eigenvector. I don't really care what the other vectors are. So let's consider V1 equal to this eigenvector V, and V2, V3, and so on up to Vn. So I'm making no additional assumptions on V2, V3 up to Vn. These need not be eigenvalues. These need not be eigenvectors corresponding to A. All that I require is that V1 is equal to V, which is an eigenvector corresponding to lambda. Right? So relative to this basis over here, so relative to this basis, what is the linear transformation A? What is the matrix corresponding to A? So we have A equal to P inverse, where P is basically V1, V2, Vn, right? And what is Bij? The ijth entry of Bij is, you take A times Vi and look at the jth coordinate of A times Vi with respect to this particular basis V1 through Vn, right? And if we look at that, so the matrix B will have the following form. Note that V1 is, so V1 is an eigenvector, and therefore B will have the form lambda 0 0 0 0. So the first column of B contains lambda in the first entry and zeros everywhere else, and then maybe you have some non-zero values here. We don't really care what it is, and perhaps all of these are non-zero values. Right. Let's call this B prime. Right. So this will be the structure of B. All that's important for us is that the first column of B has lambda as its first entry and zeros everywhere else. And right. So by this technique, we've actually reduced B to lambda and then B prime. So we're already one step closer to getting an upper triangular matrix. Now B prime is an n-1 by n-1 matrix, and therefore we can use the induction step now, and therefore conclude that B prime can be converted to an upper triangular matrix, and therefore by a similar sequence of transformations we can show that A is similar to an upper triangular matrix. Right, so there exists some Q, thus that A equal to QT Q inverse, where this T is going to be upper triangular. Right. Now, here's a question for you. What can you say about the diagonal entries of this upper triangular matrix T? I want you to pause the video and think about it. Right. So note that if you have an upper triangular matrix, then the diagonal entries are basically the eigenvalues of T. So if you have an upper triangular matrix T, then the diagonal entries of T are the eigenvalues of T. And this can be easily seen just by looking at the characteristic equation. Right. So therefore, since A and T are similar to each other, and similar matrices have the same set of eigenvalues, the diagonal entries of T are basically the eigenvalues of A. Right. So therefore, we can conclude that A is similar to an upper triangular matrix T whose diagonal entries are the eigenvalues of A. Alright. So once we have this particular conclusion, it's easy to prove the Cayley Hamilton theorem. Okay. So the Cayley Hamilton theorem says that every square matrix satisfies its characteristic equation, right? Or in other words, the minimal polynomial always divides the characteristic polynomial. So let's suppose that the characteristic polynomial of A, fa of x takes the form x minus lambda 1, x minus lambda 2 up to x minus lambda n, where these lambda i's need not be distinct, some of them could be repeated. Okay, so right now we've just seen that A is similar to a triangular matrix. So therefore, instead of looking at the matrix A, we can prove the Cayley Hamilton theorem for the matrix T, because if fa of A, so given any polynomial A, so given any polynomial function p of x, p of A equal to p of t, since A and t are similar to each other, right? So therefore, fa of t is going to be the following polynomial. It's going to be t minus lambda 1 I, t minus lambda 2 I, and so on, t minus lambda n I. Okay, and further I'll also assume that so since this t is upper triangular, let's assume that t takes the following form: lambda 1, lambda 2 up to lambda n. So the entries below the diagonal are all 0, and you can have some arbitrary non-zero entries above the diagonal. Right. Now the important property that we need in order to prove the Cayley Hamilton theorem is the fact that the vectors corresponding to which T is the important property that we'll require is that with respect to this, so the triangular for this triangular matrix, this corresponds to a fan, right? And in particular, if so you have T, the triangular matrix T, and this represents the same linear transformation as A, but with respect to some basis v1 v2 up to vn, which is a fan, right? And the reason why this happens is that Tvi is equal to lambda I Vi plus some alpha I minus 1 Vi minus 1 plus alpha I minus 2 Vi minus 2 and so on, right? So basically what we have is that T times Vi is lambda I times Vi plus some element, plus some vector in the subspace script Vi minus 1, right? And in particular, so this just follows from the fact that T is a triangular matrix and v1 v2 up to vn forms a fan basis for A, right? So if we rewrite this, so T minus, if I take the lambda I Vi on the left hand side, then this is just the same as T minus lambda I Vi is some in Vi minus, right? This is good. And so the important property that we want to use over here is this particular property, that T minus lambda I times Vi is some vector in the subspace script Vi minus 1. Okay, so what do we want to show? We want to show that T minus lambda 1 T minus lambda 2 multiplied all the way up to T minus lambda Ni, this is equal to the zero matrix. And in order to show this, all we have to show is that for every vector v in Rn, this particular matrix, let's call this Fa of t. So all we have to show is that Fa of t times v equal to 0 for all vectors v. So these two statements are equivalent, right? And but in order to show this, it suffices to just show this for the basis vectors, right? So take any basis, so that for every basis vector Fa of t times Vi equal to 0. And in particular, we'll show this for this particular fan basis over here, v1 v2 up to vn, right? So as we've just shown, T minus lambda I times Vi is some vector in Vi minus 1, right? And T minus lambda 1 I times v1 is equal to the 0 vector, right? So So this combined with this particular statement ensures that fa of t times v equal to 0. Let's see why that is the case. Now suppose, let's take a simple example. Let's look at v3. Okay, let's look at v3. So we multiply this entire polynomial over here. We multiply this with v3. But in fact, it's enough to just look at the effect of t minus lambda 1i, t minus lambda 2i, t minus lambda 3i. So let's look at t minus lambda 1i, t minus lambda 2i, t minus lambda 3i times p3, right? So we know that this term over here, so this quantity lies in v2. Okay, so this lies in v2, and therefore this is equal, we can write this as so this is sum alpha 1 times v1 plus alpha 2 times v2 plus lambda 1i times t minus lambda 2i, right? So this is t minus lambda 1i, t minus lambda 2i times v1 alpha times this plus alpha 2 times t minus lambda 1i times t minus lambda 2i times v2. Now let's focus on the second term. So t minus lambda 2i times v2, this lies, so this term over here, so this is some beta times v1 because it lies in v1, right? This lies in v1, right? And t minus lambda 1i times v1, so this term over here is equal to 0. Right? So this is equal to 0. So the second term is equal to 0. Right? So now the question is, what is t minus lambda 2i times v1? So t minus lambda 1i times t minus lambda 2i times v1, right? So this t minus lambda 2i v1, so this term over here, I claim that this also lies in v1 because after all this is some element in v2, right? So this will lie in v1, and therefore this term over here is equal to 0. So in essence, what we can conclude is that for every fan basis vector, t times vi, or sorry, fa of t times vi is equal to 0, where fa is the characteristic polynomial. So fa of t times vi equal to the 0 vector for all 1 less than or equal to I less than or equal to n, and which implies that fa of t equal to 0, or effectively if A of A equal to 0. So every square matrix A satisfies its own characteristic equation.